make your sample? How do you specify target density and how do you meet it? Okay. So so how do you compact? Is it a constant duration, like maybe 5 seconds, something like that? Uh-huh. So you report the achieved density, or do you report the target? Okay. So there are different ways, like, for example, the way I used to run it is I would calculate the target density. I know the volume of the material, and then I would say I'm going to compact in 5 layers. So I know the mass for every layer, and I know a target height of the every layer. I do not stop compacting until I meet that. Now the question is that, do you have a soft aggregate? If you have like a limestone and stuff, your aggregate may crush. That's one. Excessive compaction may crush your aggregates. That's one problem, right? Mine, where that was not a problem. I always had, so I just meet it. So it's difficult. That's what I'm saying. Your achieved density is never going to be exactly the same as your standard and modified compaction and stuff. And there is a big difference also, folks. How do you do what a Proctor test or standard compactive effort and stuff? You have a little hammer, right? What's the footprint of the hammer? It's only part of the mold, right? And then you drop it here, and if it is open graded or something, it bulges here. You drop it here, it bulges here. You try to play with it, right? So Proctor or that test is not very representative usually of an aggregate specimen. It's very difficult. And when you are compacting your resilient modulus sample, what are you doing? You're putting like a plate or something, right? And you're doing a vibratory compactor on top of that. So in this case, you are applying compaction to the entire surface, whereas in the Proctor test, you are putting only part of it. Do you see the difference in that? So the energy implied is also very different. So number of blows may not always translate the same way. So be very cognizant of these things. These are challenges. You have to have target densities and stuff. Subgrade, it's sometimes relatively easy. I have done it using the same kind of approach. You can do almost like a Marshall press or something. You can take it and then just press it. It's much easier for subgrade because you can compact, carry it to another place and set it up. It's easy aggregate. You have to have vacuum, otherwise it's going to fall apart and stuff. It's just a lot more challenging. But and either way, membranes also have a very significant effect. Aggregates, the membranes get punctured sometimes, so you have to have 2 membranes. Subgrade soils, it's much easier and stuff. So this is how it looks. Stress states 500 to 1000. Here also sigma 3s. Sorry, this looks at S because Macintosh sometimes does not read sigmas very well. This is S stands for sigma. So sigma 3, sigma D for conditioning, as you can see, it's significantly different. Look at the stress states and tell me the primary difference you see. Yes, they are different in value, but tell me 2 primary differences you see. Say that again. Yes, 5, 3, like number of stages, confining wise, it was 5. Now it's 3, right? That's the first one. Second one is? No, value is less is yes, but there is, yes, it's a decreasing pattern. You are now testing it is a decreasing pattern. There you started at 3, 5, 10, 15, 20. Now you are doing 6, 4, 2. You are decreasing. Okay. Again 15 stress states, very similar. So that was a 5 into 3. This is 3 into 5. 3 confining stresses and 5. And again, sequence numbers exactly the same, 1, 2, 3, 4, 5 and stuff. Nothing difference. You can actually have unconfined as well. As I said, I have showed you that at the subgrade level, the subgrades are such small confinement. So to represent that, to model the worst possible thing, again there is a method where they don't actually apply any confinement in the conditioning. They just unconfined, they just bang it. So it's just again torture. Remember sigma 1 over sigma 3. That's basically what I call. So this is the device that we used back in the day. My device is different. Where is MR testing now? It's a very old research method. People have been doing it very long. I am very pleasantly surprised to see so many different people have done it. How many different institutes, by the way, here? So raise one per person per institute. So IIT Bhubaneswar, just one person raised hand. Just one. Okay. Okay, let's do that. IIT Bhubaneswar. Then there is SVNIT, right? Surat. So you guys have set up as well. 2. Then there is IIT Chennai. 3. What's that? Raipur. 4. You also have a setup for that. So 4. And Burla also, Varanasi, you also have one. 5. You have one. 6. Man, that's pretty. Okay. So, but yes, most universities also have, but I don't see that many students. I guess it's a transportation geotechnics class. Yeah, I understand. But I'm very pleasantly surprised that you all have played with this. It's a very expensive piece of equipment. It's not very easy to buy at an agency level all the time. It takes a lot of time. It takes a lot of training. You have to basically babysit the thing. Like I'll show you my device tomorrow, the one that I used to use, and the specimen you have to put powder around it so that there is no friction between the two membranes and stuff like that. And my advisor used to joke is that, hey, you're far away from getting married or anything, but look, you're already taking care of babies and stuff by putting powder and stuff. So it's literally babysitting and stuff. But it's good. It's a good device. Fine grained soils. It is stress softening. So this is how, again, master students, initial PhD students, this is the kind of thing that you may be asked depending on what you are being asked. Linear elastic versus stress hardening versus stress softening. How the modulus changes, how the shape changes and stuff. Pay attention to those. How is modulus modeled? And you can do this in several different ways. So this is for fine grained soils, and there is a thing called ERI, which is something called breakpoint modulus. We'll get into that. But as the deviator stress increases, you plot it against deviator stress for fine grained soils, you'll see a decreasing trend. It's a stress softening material. There was a called the hyperbolic model. It was also used for resilient modulus versus deviator stress. Again, it depends on people. So let's step back a little bit. What is the purpose of all of these models? What are you trying to do? Why are you characterizing the material to determine resilient modulus? Is because you want to do an analysis. You want to do some kind of computation, right? And in that computation, you are going to have stress that is going to change from one point to another and stuff like that. And let's revisit that, or let's take a look at that and see what it means. In your traditional pavement design, right? Let us say this is your HMA and this is your load, right? And then the stress is being dissipated like this. Yes, the slope will change at the interface, but I'm ignoring that in this case. So you know that between this point and this point, and this point and this point, the stress is different, right? When the stress is different, that actually means that your modulus is also different. It is a stress dependent material. On the other hand, if you are doing like an ASTO design or any other design, in fact even in the MEPDG for now, you are saying that E is equal to 30,000 psi or something like that. What does this mean? Where is it? Right? In an aggregate layer, if you just model an aggregate like a very thin asphalt surface and then just aggregate and you do an axisymmetric model, you will see that in this area, this is axisymmetric, so there is a pavement on this side as well. I'm just drawing the boundary at the end at one side. So if you see, the stress actually keeps decreasing over here. So if you plot the resilient modulus heat map or resilient modulus contours and stuff, you will see that this is very high numbers versus as you go down it is very low numbers, right? So if you do that, now you are calculating your response and stuff like that. If you assume just one modulus value, and at certain points you are under predicting or underestimating the modulus, at certain points you're way overestimating the modulus, right? So you have to reflect that. So that is the reason people have a way, or people develop models to capture how I can calculate modulus knowing stress states, right? So what you can do is MR, we're going to look into that, but there is a model called K theta model, so it's basically K theta is to power. We'll get to that. Don't worry about the model for. What you're trying to say is, what is theta? We already said that, right? Sigma 1 plus sigma 2 plus sigma 3. Where do you get sigma 1, sigma 2, sigma 3 from? That's your forward calculation, your analysis, your layered elastic analysis. That's like not simple, but that's trivial stuff. You know that already. So at any point you are going to be able to calculate sigma 1, sigma 2, sigma 3, and then you are going to be able to calculate theta, and then you are going to put into K theta raised to power n, and then you able to determine modulus. But I have a question. I know what you're asking. I'm going to ask that question, so you can't ask me. How do you get sigma 1, sigma 2, sigma 3 in the very first place? To run your forward analysis, what do you need? Modulus. I thought you were determining the modulus. That's what you're asking, right? So what are you going to do now? Seed modulus, right? So let's talk about that a little bit. So it's a little bit deviating, but I'm glad that you all, most of you are at least following up. So let's go there. I like this discussion. So I am going to assume E is equal to 30,000 psi. Okay? I'm going to run the forward calculation, like layered elastic, LET, layered elastic theory is what it is, LET. I run it. So at every point I'm going to get theta now, sigma 1, sigma 2, sigma 3, right? Now I can get, from that I will get MR distribution at all the points, right? And then that MR I'm going to calculate, let's just say that MR at a certain point, maybe at the midpoint, let's just say my target is the midpoint, that MR comes out to be 35,000. Let's say it comes out to be 35,000. I started at 30, so I rerun this with a value of 32,500, which is midpoint of the two. Then I again calculate theta. Then I again calculate resilient modulus. Then there is a difference. I take again average. I again run it until I converge. Then I know this is my right representative modulus value. right? This is what you are doing in LET, layered elastic theory, because you are assigning only one modulus per layer. Life becomes very easy if you are running something called a finite element model, because now your values can change every node, right? And we'll get to that. We'll do on day 5, we will do ILIPAVE. You'll see what it does, and you can actually plot. Are you following what I'm trying to say? Modulus is not that easy of a thing to chase down in unbound materials, right? It's a little bit tricky. You have to iterate. Okay, most most subgrade soils, if you plot the resilient modulus against deviator stress, okay, you see a kind of bilinear behavior. Okay, now some people call it bilinear, some people call it piecewise linear. I'll leave it to the mathematicians to decide what it is. I have always called it bilinear, but recently I have been taught on completely different topic that it should be piecewise linear, not for this, but basically until a certain point, which is called break point the deviator stress, and from experience it is close to about 6 psi, just empirical, there is no physics behind it, it's about 6 psi. Okay, you have a very rapidly reducing modulus. Beyond that it goes a little flatter. Okay, so there are bilinear models. We'll take a look at models. So this is how the model looks: k1 plus k3 k2 minus sigma d when sigma 3 is less than k2, k1 minus k4 sigma d minus k2 when sigma d is greater than k2. It's basically just, this is just defining the two equations, no rocket science in it. And when we play with ILIPAVE, we will look at this in detail and you will know exactly what's going on and what not. Okay, by the way, you have seen some places the ERI, and I said I will tell you later, the ERI basically is this break point modulus, this k1 value. At what point is the modulus breaking? It's just in subgrade soils they use. Okay, so this is again couple of North Carolina airport, some tests and stuff. You can actually fit bilinear models. How do you fit the bilinear models? You just do it like eyeballs and stuff. You just see these are in linear. You just see these are linear. You don't, there's no defined break and stuff. Other MR models for cohesive soils, again we're going to skip through these very quick because we're not going to use this. I want to get to the models that we are going to use so that we can spend some time on it. This is Brown's model. PQ, anybody you know, advanced geotech classes, you know, stress paths and stuff like that, right? You have taken classes. We're not going to get into that. Stress paths, you know, and stuff. That's PQ models and stuff. This is Dawson Gomez Correa model. Again, when I give you the slides, you will have it for reference, but you know, I have never used this in practice myself. Empirical correlations, you have seen this: 1500 CBR, 17.6 CBR, 0.64, 1155, 555 R, ERI is with QU and everything. This is again, folks, let's see your memory. What level of MEPDG is this going to be? Mechanistic empirical, I said there are 3 levels of designs, remember? What? This is 2. This is 2, right? You test something and you are predicting something. That's what this is happening, right? But again, I think by now you all know we should not be using CBR to predict MR because it's a different test, blah, 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 all of that. But when you don't have anything, you have to. Just have to, right? What are the primary factors that affect behavior? You know, sigma D, sigma 3, moisture content, plasticity index, clay content, high density, freeze thaw effects, you know, they affect your behavior quite a bit and stuff. Some results, I'm going to skip through this because we're going to get into models now. Moisture effects, again, if you see wet of dry of optimum, it's very high. as water increases, its status collapse stuff. So it's just standard observations and stuff. Let's go unbound granular materials. I told you this is stress hardening. This is what I was trying to get into when I told you, and we're going to see this on Friday. We're going to do this on ILLIPAVE. You will do it on your computers, and you will see this. Look at how the modulus at the so this is an axisymmetric, so load is right here somewhere at 0, 0 basically. And if you see, this is a 400 KSI asphalt, this is 28,000. As you move away, it is about 10,000. So this is the range of change you can see of resilient modulus when you are trying to study the variation inside. Okay, so constant value is not necessarily a right thing. Now we are going to look into models. The very first model is sigma 3 versus resilient modulus, kind of K times resilient modulus, and for the tutorial this is a good time for me to start telling you how to do this. Let us say, and again disclaimer, this is not a model that you are going to use all the time, this is very rarely used model, but let's say this is the model we are using. So MR is equal to some kind of a constant K1 sigma 3 raised to the power K2. Okay, people who have done this, please don't answer, because you probably know this already, you have done it. I want the others to brainstorm a little, and I want this, folks. I give you a resilient modulus test data, like a test result, and I tell you that I want, for my analytical model, for my finite element model, I want this model form, give me the K1 and K2 values. How will you approach this problem? And people who have done this, please don't answer. I want the others to have a discussion here. How do you think we should approach this? Umesh, in your class, did you go over model fitting and stuff in your? No. Okay, good. So people. Okay, but you didn't tell them how to go from the test result to model fitting, or did they do that? Okay. Okay. So we'll okay. So now we are talking about a test data. So does everybody understand the question? What I'm saying? You have a test result. You have a full test result, and now I am asking you, give me K1 and K2. How do you think we should approach the problem? Yes, but how? That's the exactly right answer. But how? How do you develop the correlation? The first step you said, elaborate that. Teach me how to do that. Okay, okay, you going ahead, but I'll go with you, because we are not there yet. But okay, log MR is equal to log K1 K2 log, okay, y equal to mx plus c. This is c, this is x, this. That's what you are also saying, right? And then what do you do? We have the data point. How many data points we have? 15. We have 15 data points, right? So we have 15 data points. So you are taking the MR, then you have sigma 3, fit a linear equation, log blah blah blah, you do that, and then what happens? So K1, so this is basically C, so C is equal to log K1, so K1 is equal to 10 raised to the power C, and stuff like that. Easy. Everybody? Viswandita, did you follow it? I want the undergrads. Pushpak, are you okay? or MTech, just first, did you follow this? Please continue, because we are going to do this in tutorial. So let's slow down. What do you have in your MR test results? You have all the stress states that did you apply it or did you get it? Applied. Stress state is something you apply. And what did you get? MR. So you have MR and sigma, all the sigmas in your test result. And how many do you have? 15. Right? So you are going to say, I am going to plot log MR versus log of sigma 3, and I am going to fit a straight line to it, and my model formulation says it should look something like this, and I am going to just decode the parameters, model parameters. Good. Then that is y equal, then we have K1 and K2. So that's basically what is going on here in this case. You find K1 and K2. Now you have a beautiful thing with you. You are like, here is your K1, here is your K2, now go and run wild. Run any layered elastic analysis, determine sigma 1, sigma 2, sigma 3 at any point you want, put K1 and K2, that's the modulus at that point. Right? So now you have a complete distribution. So that's this one. The most common one is called the Hicks and Moniz-Smith model that you will come across all the time. It's called the K theta model. K theta model. Theta, as I have already explained to you, is bulk stress. Sigma 1 plus sigma 2 plus sigma 3. And you are plotting it against theta and MR, exactly the same thing. You fit your model. Instead of this, now this becomes theta, this becomes theta. Right? Question? Please ask. I don't have a problem going over this again. Go ahead. Oh, here you're saying, why is it doing that? That's a good question. I'm glad you caught that. Why is it doing this, folks? This is sigma 3, right? You're talking about 1 psi of sigma 3. That's the log. It's a log scale, but it's 1 psi, and the minimum theta you are applying is probably about 4, 5 or 6, because theta is sigma d plus 3 sigma 3, right? So you're already on the right hand side. Good catch, but yeah, it's just the nature of the value, nothing special. Are we good on this one? K theta. What do you think is the problem with the K theta model? Again, people who have done this, who have studied this, don't answer. But if you have not, everybody is open. Can you say that again? Yeah. I mean, if the data, I mean, the model is in log, so that's why it's a straight line. It's in log scale, by the way, right? So it's the same thing, K theta to the power n. Here is my question, folks. Theta is sigma d plus 3 sigma 3. Let us take with a stage sigma 3 is equal to 3 psi, sigma d is equal to 1 psi. So what is theta? 10 psi, right? Second stage, sigma 3 is equal to 1 psi, sigma d is equal to 7 psi. What is theta? The K theta model, the modulus value is same. Is the material going to behave the same? Which one is it going to be stronger? much more confined, right? So in the k theta model, you are not able to isolate between the effects of confining and deviatory effects. Do you understand what I'm saying? It works. K theta model works all the time. It is the easiest model to use. It is the most common model to use, but there is a limitation. It doesn't isolate the effects, because the effect of confining versus the effect of deviator is different. Like what they just said is, for a cement stabilized thing, I'm quoting them, I did not test it, but the effect of confining is very limited. Deviatory, you see significant effect. In the theta, you can't distinguish that, right? Because it's merging everything into theta. So how do you address it? Pavitra, right? How do you address it? See, these are open-ended questions, so you just shoot for the sky. You just get anything you want. There's no answer I haven't given you, right? How do you address this question, problem? You can phone a friend if you want. Anybody? 3 parameter? Say again? Maybe confinement as a separate parameter. Let's do that. Let's do that, and then I will ask you a question again. K1 times, they are saying sigma 3 raised to the power K2, then theta raised to the power K3. Is that what you're saying? Ah, now we're talking. Now you're separating them, right? So my answer is yes, exactly. You have to separate somehow. But let's not get there yet. There is actually a model called the Uzan model, which we will take a look in a second. Sigma d raised to the power K2, theta raised to the power K3. Professor Jacob Uzan, the smartest person alive in pavement engineering, by the way. If you ever get a chance to interact with him, you'll see. He's from Israel. He's a walking genius. Developed this. I have a very interesting story about Jacob Uzan, I'll tell you. So when I was a grad student, there was a conference at TRB. You probably have heard of TRB. So we were sitting, and there is a lady who made a presentation from Texas A&M University, and not a faculty, a postdoc. She made a presentation, and she kept citing some work that Robert Litton or Bob Litton, that's another name if you in pavements you'll read all the time, Bob Litton and Uzan had done. So she kept citing that, Litton and Uzan did this, Litton and Uzan did this and everything. So finished the presentation, and this old man stands up and he says, can you go back to this equation? I don't think the equation is derived this way. And the lady's answer is, no. Dr. Litton and Dr. Uzan did it this way. And he's like, I am Uzan. I did not do it that way. And the funny part is, of that postdoc was sitting right there next to me, actually. And that's it. He was sitting right to me, and he could not say, it's a room full of people. And he's like, that is Uzan, you idiot. That's Uzan, right? So finally Jacob says, I am Jacob Uzan. I did not do it that way. But anyway, so yeah, those kind of things happen. But what Professor Uzan did is he separated this, right? He just made k theta into a 3-parameter model. There is a little challenge with this one. What can you think? Yeah, it's overfitting a little bit, right? Because theta already has sigma d in it, so you're kind of using it twice, right? But there is some reason that I don't know that it was done like that. Oh, by the way, this is just k theta data. We'll take a look at k theta values very soon. Actually, maybe we should cover a little bit here. You can have representative values for k and theta. general trend is that as theta increases, or sorry, as k increases, n decreases, you kind of have a reverse trend, uh, and and so you can actually predict kind of. So in my dissertation, I should have had that plot actually. So this was by Professor Matt Witzak and Gonzalo Rada back in 81. They actually had a R square of 6.68, but as I said, my PhD dissertation was all about, you know, aggregate testing and stuff, and it was a limited data set. We used Illinois aggregates, but we had about 270 data points, and we had a R square of about 0.92. So if you have a consistent testing effort, you can actually predict n from k. It's actually a pretty nice reverse correlation. As k increases, n decreases, you can actually predict materials. It becomes very important when in modeling and stuff. So this is Higgs and Monismith, and then Professor Uzan changed it. Theta, oh, I probably wrote it the other way. That's fine. It's just two different parameters. One is theta, one is sigma t. Yes. Yes, right here. Well, there must have been a reason. I don't know the answer to that, so I'm not qualified to answer. I mean, they probably tried to isolate thing or to separate the sigma d effect, because okay, I kind of know the answer, but I don't want to say it very strongly. So deviatoric is a standalone effect, whereas bulk stress is actually the whole thing that helps with confining. Like what I'm trying to say is sigma 3 is not the only thing that helps the specimen. It's the entire bulk that helps the specimen. So you can think of it as sigma d is the torture component, as the other component is the helping component. That's how he tried to isolate it. But yes, it is a little bit of an overestimation. Then in UT Austin, they separated it into sigma d and sigma 3. But honestly, the Uzan model is actually much more used than anything else because of the bulk effects and stuff. Again, this is just fitting of data. We'll do that this afternoon, so I'm not really spending time on that. This is what I will show you. I'll show you a MATLAB code that I had developed when I was doing my PhD. For all my test results, for everything, I used to like model. I used to fit like, you know, k theta model, Uzan model, MEPDG model, which we'll get into and stuff, and we used to do some relationship in that. Oh man, this is not looking good. Let me see if I can. Give me a second, folks. If I can boot it on Windows. Otherwise, it's going to look. Okay. So, oh, this is a good point for us to discuss something, because we're going to get into model fitting. So let's do that right now. MR is equal to k theta raised to the power n. What is the unit of MR? Say again? Megapascals. Good job. What is the unit of theta? Megapascals? What is the unit of K? Okay. Is your equation right? Why not? Dimensional inaccuracy. Right? I mean, no matter what you do to K, it cannot take a square root like raised to the power 1 over n for this, right? So what the heck is going on? Yeah, but you still, I mean, yes, they are empirical formulas, but they are still, representing stress strain behavior and stuff. So how do you address this? Make theta unitless. How do you do that? Okay, so now he's talking. So either P naught or PA or something. Now you're doing n. So now what is the unit of this ratio? Unitless. So what now happens to the unit of this? Kappa, MPA, or whatever, right? So pay attention to this reporting your test results. Right? When you're writing papers, when you're writing tables and stuff, make sure this is consistent. Blindly say K is unitless. If it is K is unitless, your model is wrong. Right? So these are little things. This is called nitpicking, but you have to be particular about these kind of things, right? Another thing I think what Akshay said is you can also develop divided by PA. What is PA? What is the value? 14 point? Is it 3 or 7? Is it 3? I don't remember. I think it's like 101.3 kPa, right? Whatever that is. I don't remember exactly. But just remember this, that if you, both are correct approaches. Theta K theta, you always do P0 because you divide by 1. Otherwise, you do realize that your model parameter values are going to change, right? Whether you divide the theta by 1 or whether you divide by 101 or 14.7, your model parameter values are going to change. So just pay attention to what you are trying to do. So for K theta, it's more common to have divide by P0, which is 1 kPa. Just the same. You're just making it unitless. Okay. Then there is something called Leyden-Nelson's model. Again, I1 is the same as the first stress invariant. J2D is basically the octahedral tau shear stress. We'll get into that. Octahedral shear stress is again another mechanics thing. By the way, who can answer me senior PhD students or whatever question? What is a stress invariant? No, that is first stress invariant. I said what is invariant? With no, I mean invariant is an invariant. I mean it can be summation, it can be expression or something, but the question is it does not change with change in the coordinate system or something like that. Whatever you do, it remains the same. The magnitude does not change, right? So that's what first stress invariant is. So tau octahedral is another definition that comes from mechanics, okay, and it is defined as 1 over 3 root of sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. Okay, now let's do it for a for a triaxial, typical cylindrical triaxial test, what is sigma 1 minus sigma 2? Sigma d. What is this term? Plus what is this term? So 1 over 3 times 2 times sigma d square root whole thing is square root 2 over 3 times sigma d. That's called octahedral shear stress. Okay, that's also sometimes written to as the J2D. Okay, that's what this is. Oh no, no, J2. I think there is a problem here. It should be Q. It should be J2D is Q square or something. But anyway, it doesn't matter. What matters is some of the models have tau octahedral in there. Okay. Now we are trying to see what is happening. There is this thing called universal model. So now look at this. It has a theta component, which is bulk stress component, which is helping the system. It's a tau octahedral component or a shear component, because remember, tau octahedral in a cylindrical thing is nothing but a sigma d. Is the torture component. It's the deviator stress component, right? And that's the shearing. That's what's hurting the system, right? You're isolating those two. And then this is also P0. Then they changed it a little bit to MEPDG, where they did this, and then they introduced PA in here. Okay. There is a term here, +1, that magically appears. Okay. And I'll give you a hint. The existence of a +1 is a very funny reason. It's not a scientific reason. It's a very funny reason. Tell me what. Yeah? Yes. Whole equation collapses. Your resilient modulus becomes 0. So it's an artificially cooked way to make it non-zero. Right? It's not based on mechanics. It's based on mathematical manipulation. Right? This is called the MEPDG model. Okay. In our tutorial today, we're going to look at all three. We're going to do K theta. We're going to do Uzan. We're going to do MEPDG. Question, Atanu, were you raising your hand? No. We're going to raise all of that. Okay. And in this case, look, pay very close attention to your model formulations. There is a PA here. You are multiplying PA. So what is K2? Unit of K2. Sorry, K1. Unitless. If there was no PA, what would it be? Megapascal or something, right? Pay attention to how the model is defined. I see a lot of times in literature, people just coming up their own version of things and stuff. It's not fair. You have to give credit to people how defined it the way it should be defined, and then pay attention. Any questions about this? Straightforward, right? We should be able to fit models. Level 2, design, right? What is level 2? We have something else and we are going to predict, right? So correlate from empirical lab tests, obtain MR from CBR, which is 55 plus 555 R or 2555 CBR raised to power 0.64. Obtain MR from PI or gradation properties, convert agency layer coefficient into this and stuff. So now you are trying to relate structural coefficients into resilient modulus, which is a little bit of a far too fetched. But again, if you don't have anything, you have to do something, right? I don't agree this is really level 2, because A is not really that you are determining by testing anyway. A is kind of an iffy parameter. There is DCP and CBRs. There is level 3 where you don't have anything. You have like A7, like AASHTO classification, or just subgrade soil properties like a geological survey or something, like for this I'm going to use this, right? It's basically like, you know, all cars are red, right? So it's basically it's very far-fetched, but you have to use something, right? So that's factors affecting MR, primary factors. It's stress dependency, so applied stress states, sigma 3 and sigma d are very, very important, and then all the other factors like dry density, moisture content, fines content, right? Freeze thaw effects, it collapses and stuff. Again, for different, this is what I tell is extremely carefully developed, you know, empirical correlations. Like, yes, these are absolutely empirical, but they are now, you know, including water content, and they're now including dry unit weight and stuff like that, whatever they have found. It's not really purely mechanistic, but there is also a theta effect and stuff. Okay, so this is actually from one of our studies at Illinois. As water content increases, aggregate base with 12% fines, as the water content increases, it starts collapsing and stuff. So you have to really pay attention to moisture content. Moisture is the biggest enemy for your unbound materials. Okay, angularity, as the percent fracture faces increase, your resilient modulus increases. Its angular interacts much better and stuff like that. Okay, crust and unit weight. This is just errors. Repeated load triaxial testing. This is neural network stuff. Let's not worry about it. Crushed gravel versus crushed aggregate versus gravel. Tanmay was asking me yesterday. See, this gravel is basically river gravel, like river pit gravel. It's not crushed. You just go to a river pit, you excavate, you grade it, and that's it. That's how it's sold. It's natural gravel and stuff. So it's very rounded. So as the crushed material increases, your resilient modulus increases significantly. Versus at the blend, you actually have somewhere in the middle. So this is actually one of the studies that was said is, if you really have to use uncrushed material, at least blend it with some crushed material to increase your response. I mean, improve your response. This is my PhD study actually, Mr. Antutumler. This is actually gravel with 0% non-plastic fines, optimum. Limestone with 0% non-plastic fines at optimum. And as you can see, this gravel is again an uncrushed gravel. So it's actually much flatter at the bottom. The crushed material gains much more stiffness. Stress hardening effects are much bigger and stuff. This is another angularity. This is the dissertation I sent you, Tanmay, the Tongyan Pan's work. And this is basically angularity and surface texture. As the angularity increases, so we haven't talked about this, but you know, aggregates, the angularity, there is a way to quantify it by image processing. It's called angularity index. We'll not go into the details. Higher angularity index means it's a very angular material. Lower means it's uncrushed kind of stuff. So as the angularity index increases, resilient modulus increases significantly. As the surface texture increases, now we are not talking angularity, but I am talking now the roughness of the surface. That also increases your modulus. So you see that significantly here. This is something related to modular ratio. I'm going to skip this for today. We're going to talk about anisotropy later. This I don't want to get it lost into anisotropy. This is another thing. Higher fines. This is again 4% fines, 90% of optimum, 16% fines, 90% of optimum. So the same material. So this is all engineered gradation. So my the year of 2006, the entire Christmas time, like from November mid to mid January, I was in a sieve room sieving like maybe 2 or 3 tons of aggregates. That's all I was doing. So this is all engineered, like every aggregate. So 3 aggregates, limestone, dolomite and uncrushed gravel, they were separated into big drums by size. So I would basically take 2-3 shovels, sieve it, separate into drums, keep doing that, and that is what my entire PhD was on. So this is all engineered gradations. As the amount of fines increases, because fines are fine grained stuff, not coarse grained, so you're not gaining as much stress hardening. So a low percent fines, your material is more stress hardening. As you start inducing more fines, it actually reduces the stress hardening property. So that's what this is. This is aggregate layer stiffness. You know, it's a nonlinear function of applied stress states. And then advanced aggregate testing, we need to determine what is called as directional dependency. Okay, what happened here? Why is it not changing? Okay, so we have about half an hour, right? Yes, exactly. I think this is something we can get into. Okay. Mesh, so this has a continuity. Okay, I mean it's a lot bigger. So what I am thinking is, maybe in the next 30 minutes we will start looking at the models and stuff, and then continue that into the tutorial and the back calculation today, so that this we can cover tomorrow. Is it okay? Yeah, I mean everybody is here. I mean, yes, it's being on, because this models and stuff is going to be a lot more hands-on, so it's for the online people, it's probably not as beneficial and stuff, but we can do that. I don't want to spend half of it today, or maybe I can just give you the concept. Yeah, let's do the concept. I don't want to change the pattern. Okay, let's revisit this, folks. Who remembers what did I say the concept of sigma 3, sigma x and sigma v? What was the relationship yesterday? We talked about this. No. Inequality in a triaxial, in a typical triaxial testing. This is what? This, right? But we said that's not always the case. There is going to be extension states and stuff like that. So that is where this advanced triaxial testing comes into picture. Okay, and we are going to separate this now. So I'm going to draw the same sample now, but I'm going to separate this quantities. Here is what I'm going to say. I'm going to say this one, I'm going to say sigma h comma static plus sigma h comma deviator. Okay, and this I'm going to call sigma v comma static plus sigma v comma deviator. Do you understand what I'm saying? Right? Until yesterday we were just talking this at sigma h horizontal, and this we still had kind of sigma h or sigma 3 plus sigma d, right? Now I am not worrying about sigma 1, sigma 3 or anything. I am talking horizontal, vertical, pure separation, and I am saying some magical way I am going to say there is a static and there is a deviator component here, and there is a static and there is a deviator component here. Does that make sense what I am saying? Okay, now what I am going to do is, this is probably going to be a good exercise. Let me see, hold on. Instead of washing, it's probably better to drink it. Okay, So now we are talking about a specimen. Okay, I somehow come up with a magical way of having a sleeve like this. Okay, and my specimen is in this sleeve. Do you understand? The triaxial specimen is in the sleeve, and I have a magical way of separately applying vertical stress here, and I have a way of confining it this way, right? Now you see the difference. In the past, what we used to do is we used to keep it in a chamber, so the same air pressure was confining all the way. Now I am separating it, because the way, why, when it was the same air pressure covering, I had no way of making sure that the horizontal is greater than the vertical, because at least the vertical is feeling the same as the horizontal. Now I am separating it. I am now holding it this way. So now if I am holding it, I can squeeze it this way, can't I? And if I have a separate mechanism here, I can pulse it separately, can't I? Now you see that there is independent control over the lateral and the vertical, right? So when I do that, now I am getting one step beyond our conventional triaxial testing, right? So the test method we are going to get introduced to now, it's called the University of Illinois fast cell. That's basically the concept. This cup is this box. It's a cube. The cube is full with oil, hydraulic oil, and inside that there is a membrane, and that membrane is basically creating the effect that my hand is just creating. And there is a actuator which you don't see at the back connected to that oil, where I can pulse it, pressurize the oil so that it squeezes the sample. Do you understand? And the vertical is just a vertical. I mean, any, just whatever you have seen, what you have done, right? Now what can I do? If I want to run a standard triaxial, conventional triaxial test that you have been running, and we're talking resilient modulus, not shear strength, resilient modulus, what should be the relationship between sigma Vs and sigma Hs? S stands for static. They are the same, right? So sigma Vs is equal to sigma Hs, and what is sigma Hd? 0. And what is sigma Vd? That's your conventional triaxial testing, right? But this is just one special case. I do all sorts of fancy things on this, right? This completely opens me up for everything I want to do. I can set sigma Vd is equal to 0, and I can pulse this thing in the horizontal direction, right? Why is this important, folks? What did I say? When the wheel moves, what happens to the principal strain's direction? Moves, what happens? To test it in the lab, you would have to rotate your specimen. How possible is that? It's not, right? It's an unbound specimen. You can't make it horizontal, it's going to collapse. So might as well develop a test system which has independent control in my vertical and horizontal, and now I can do everything and anything I want, right? That is this advanced triaxial testing called University of Illinois fast cell. That is basically what, you know, my advisor and somebody else came up with, and this is what they won their awards on. And essentially he has made like a majority of his career based on work like this. These are some inner views. So this is the actuator in the horizontal at the back. You can just push it. This red thing is the dummy specimen. It's the specimen inside the sleeve, not the sleeve, the specimen inside the sleeve. The chamber is raised, that's in the air right now, and you just get it inside, and that is what I was powdering. Remember I told you that I had to powder my specimens because there is a membrane on this and my specimen is in there. So the membrane to membrane friction I have to reduce, so I have to powder the specimen all the time. Otherwise it's going to collapse and stuff, it's going to shear. So you do that, and then that basically gives you complete independent control over, look here, the sleeve, just like I did, does not extend to the top, because if it extended to the top it beats your purpose. You need to have independent control over radial and vertical directions. That is the reason this is separately applied, and now you also have radial LVDTs. I can actually apply a radial deviator stress and measure a radial recoverable strain, and I can actually define MR, H, horizontal resilient bacillus. Why is that important? Let's think about aggregates. Now let's go back a little bit into mechanics and classic elasticity and stuff like that. There is a thing called isotropy. What does isotropy mean? Same in all directions, same property in all directions, right? That's true for an aggregate layer. No, because when you compact an aggregate, the particles actually arrange something like this. Right? So if you apply this way, they are sitting on each other and they're resisting. If you apply this way, the behavior is different. So it's called anisotropy. But is it 100% anisotropy? It's still a cylindrical specimen, right? So the horizontal, the x and the y directions are probably similar, and they are different from the z direction or the z direction, right? So there is anisotropic this way and anisotropic, like one set of properties this way. So it's called cross anisotropy. It's not truly anisotropic, it's not three-way, it's called cross anisotropy. So the fast cell represents or models cross anisotropic behavior. You are not differentiating between sigma 2, sigma 3. If you did have a true triaxial system, which is a cubical thing, you could do that. I think Professor Buddhima Indraratna in Australia has a true triaxial for railroad ballast, if I remember correctly. I haven't seen it, I haven't been to Australia. This is the science behind it, folks. Epsilon 1 is 1 over mr sigma 1d minus 2 times nu sigma 3d. Do you remember this? What equation, what formula is this called? What law is this? Poisson's effect, but what law is this? Hooke's law. This is Hooke's law, right? This is what you have seen. So when you do vertical, and epsilon 3 is 1 over mr sigma 3d 1 minus mu minus nu times 1 minus sigma 1d. This, now look, there is a d in both directions, right? When vertical pulsing only, sigma 3d is 0. So this term becomes, so sigma 1d over mr is epsilon r. Isn't that what you are working with to start with? Yes? But if you have epsilon, and in that case sigma epsilon 3 is just the Poisson's effect, right? Just the Poisson's effect. Horizontal pulsing, epsilon 1 is minus 2 nu times this, and epsilon 3 is the 1 minus nu component. It's just Hooke's law interpretation. there's no difference. But what you do see is, look at epsilon 3 in vertical pulsing and look at epsilon 1 in horizontal pulsing. What do you see the difference? Gets doubled. Why? Say again? Yeah, because x and y, there is a 2 as well, which we are not counting here, right? There's a 2. It's a three term equation, right? That's why it's happening this, right? So this is the advanced triaxial testing concept of pulsing it in different directions. Okay? So this is CCP m equal to 3. This is basically the standard testing, and what you can do is you can have sigma. Look here. Now deviator stress is written as sigma nd. It doesn't say V or H, it's N. It can be anything. You can pulse in any direction, right? And then you can actually see things like you can do the testing approach, checking and stuff. And I actually did the exact same thing, and this is on the red specimen. This specimen, it's plastic. It's like not plastic, like synthetic rubber or something. So is it dependent? No, it's constant modulus. So irrespective of which way you pulse, you should have the same, and it's isotropic, right? That's what this data is saying. You're proving it that either way you pulse, you measure the same thing, right? Then the fun starts, right? Now you are talking about MRV is the closed and MRH is the open. Now you're talking vertical modulus and horizontal modulus. Now you're quantifying anisotropy, cross anisotropy. Why is that important? I will tell you when we go into modeling and stuff, right? Now the fun starts. Look at this and look at this. So the horizontal is significantly lower than the vertical, right? What are you doing when you are modeling in layered elastic or traditional FEM and whatever that? You assign the same, right? So you are significantly over predicting, overestimating the horizontal modulus. So you are significantly under predicting the responses. When you consider anisotropy, your response will be lot. So you're like, oh my God, my finite element model, which is really fancy, is giving me 100 microstrain, but in the real world I'm seeing 150 microstrain. Why? That's because you are assigning the same modulus in vertical and horizontal directions. It doesn't work that way for an aggregate. It's anisotropic. You have to separate it up, right? Very, very limited implementations, purely research. I mean, it's not been implemented into practice, but this is what that Fred Burgraff Award paper he won back in '99 and stuff for this. This is what you have seen already. Stress path is rotating. Measure principal stress, how it is rotating, what is the degree of alpha is the rotation. You have seen this already, the extensional state and stuff like that. And you can measure and predict all of that or simulate a lot of that using the fast cell. Okay. Now look at this. This is actually from the FAA, Federal Aviation Administration in New Jersey, Atlantic City, New Jersey. They have a huge testing facility. It's called NAS, National Airport Pavement Testing Facility. It is actually one of the major researchers in there is actually an Indian guy, Navneet Garg or Nav Garg. He's a very, very well-known person, another Illinois graduate. But if you see here, these are pressure cells, vertical, horizontal, and these are the states. You can actually see this is real data. This is not theory. This is not schematic. Look here, you actually are seeing extension of these materials. There are stages, time history, where you actually record higher horizontal stress than vertical. So you have to somehow be able to simulate that in testing as well. So that's what the advanced triaxial testing is. This is the QP diagram. We're not going to go into this, how you are going to get into the length of stress path and slope, and what is the slope of the stress path when you are testing because you have the independent ability of controlling the two stresses. You can simulate any stress path you want, right, in there. So this is sigma 3 sigma 1, and then it changes as you apply more loads and stuff. So then you can actually test it differently. For top of base, for middle base you can actually rotate it, bottom base you can actually rotate it and stuff, and you'll actually have different stress sequences. So this is variable confining pressures, this is constant confining pressure and stuff like that, which is your Astro T307. Same here, you can do it in vertical. This is the VCP, variable confining pressure. You can actually in a PQ diagram. So by the way, this is the definition, just so that you know. And I think, okay, I think for PQ there are two definitions. I think one is called the MIT definition, one is called the Cambridge definition or something. I don't remember exactly. It's been a while I have gone through this, but this is the definition we are talking about. So Q is nothing but deviator stress essentially, and P is bulk stress divided by 3. So average mean stress is what they call it. And if you want to run it, you can actually test the materials in horizontal pulsing only. It's actually pointing down at a slope of 3:2. If you do a vertical pulsing only, it's pointing up at a slope of 3:1. So now you are really playing with the stress path of the material, what it is subjected, what it is and stuff like that. This is stress path dependency. I think we can skip these. Let's see what else. That's okay, that's actually good. So 1254. So this is pretty much what I wanted to touch on, this concept. And tomorrow, like today we'll do the modeling on the vertical and the back calculation and everything. Tomorrow I will show you some data for horizontal pulsing, and we'll try to take a look at how that works and stuff like that. So we have 6 minutes. So any questions or any discussions before we break for lunch? How did we evolve into that point? And so the point is the background or the entire derivation of this is from a theory of elasticity and classical mechanics point of view. And in classical mechanics, deviator stress does not really exist, right? So is the octahedral shear that is actually affecting the shear. It just resolves down to sigma d in traditional triaxial testing. You can't derive a theory for that because it's a very simplified case. So they derived the theory for the full case, which is classical mechanics or theory of elasticity is octahedral shear stress, and then it just resolves down to deviator in triaxial testing. Anything else? Does everybody, we still have 4 minutes, 5 minutes. Everybody has their computers available, right? So let's do quickly. I'm going to show you a link. I'm going to send you a link right now. Let's download or let's visit that link. So go set up your laptops so that we can be productive in the tutorial. Okay, we have a couple of important things to cover in the tutorial today. આપણે બંધ કરી દઈ પાડ્યો સેટા લાઈવ સોરી બંધ. What is anywhere, right? So think about it this way: if the horizontal modulus underestimated or overestimated? Overestimated. So if you assume it is isotropic, so the material is equally strong this way and that way, right? So now if I have a component of stress acting this way, my strain, like you can do a cosine theta and a sine theta. So this component, the strain is in a very simplified way stress divided by modulus, and now you are dividing by a very high modulus. So you are under predicting the strain. Are you following? But if you actually do the real estimation, the strain will actually be higher. So, and what governs, what does strain govern? Your actual performance, like cracking and everything is coming from strain. So what I am saying is, by under predict or overestimating the modulus, your estimated performance will actually be better than what you will see in the real world. That answer your question? No, no, okay. No, well, no. There is a difference. You are not considering tension, right? Horizontal strain, I mean, the way you define it, horizontal strain does exist because the material does deform, does get displaced and stuff. What we are saying is that it does not resist deformation in this thing, which is called tensile stresses, right? So, but the point is, the entire system evolves or behaves based on components, right? It's acting at angles, and when you are resolving it, this does not only affect this also affects this, right? Because that's the Poisson's effect. When you are applying something here, it's going to go here as well. So what I'm saying is, the composite wise, it's not going to be correct. Okay, folks, what I want you to do is